Today we're going to look at the end of Unit 5, which is 5.3 about bond enthalpies. So bond enthalpy, you have to understand that it takes energy in order to break a bond. So bond breaking is the energy needed to break 1 mole of the bonds. Notice that it's in a gaseous molecule under standard conditions. Now, not all of our bonds are identical, so we tend to compare them and use average bond enthalpies. So for example, oxygen bonded to hydrogen in water is going to be a little bit different than when it's bonded in ethanol. So that's why we use average bond enthalpies. So what we do is we take the oxygen and the hydrogen, break that bond into just oxygen atom and a hydrogen atom. We're not forming ions, we're simply breaking that bond. And it is an endothermic process. Since it requires energy to break a bond, it's endothermic. Now so a triple bond tends to have a higher amount of energy needed to break it because there's more of those shared electrons. Remember, the more electrons you're sharing between two nuclei, the shorter the bond length is because there's more attraction. And so the more attraction you have, the more energy is needed to break that bond. So on the product side, you have bond forming. So that's the amount of energy needed to break a bond that's released during bond formation. So instead of requiring that amount to break the bond, that amount of energy is being released when that bond forms. So bond forming is always an exothermic process. And we can use that when we talk about a reaction because we can look at what is the overall need to break those bonds in the reactants, and then how much energy are we getting out from the products in our bond forming. Exothermic reactions have a stronger bonds being formed than broken. So not as much energy is required to break the bonds than is released when you form the bonds, and vice versa in endothermic. Endothermic requires more energy to break the bonds than you're going to get released when the new bonds form. Bond enthalpies are given to you in section 11 of your data booklet. So anytime a question refers you to that section, or if the question says bond enthalpies as opposed to bond formation, enthalpies of formation, then you're going to use bonds broken minus bonds formed. So it's really important you understand when to use this. You're using bonds broken minus bonds formed when you are given bond enthalpies. If you're given enthalpies of formation, then you want to do products minus reactants. When it refers to bonds, you're going to do bonds broken minus bonds formed. So let's look at an example. We're going to do 3 examples. We have CH4, methane, and it's combusted. So we need to first write the reaction, and then we need to balance that reaction. So the carbon is balanced. Hydrogen, we would then need to put a 2 in front of the water, which gives us 4 oxygens. So we would need 2 oxygens as well. So there's our reaction balanced. Now to look at the bonds that are broken and formed, you need to draw the Lewis structures. So if you don't remember how to draw Lewis structures, you're going to have to go back to Unit 4 and review how to do that. So for CH4, you add up all the valence electrons. You're going to put carbon in the middle. You're going to bond everybody to carbon, and then make sure the outer atoms are satisfied. Hydrogen automatically is because it only needs 2, and you have your Lewis structures. Oxygen diatomic forms a double bond. You have carbon dioxide, which will have a double bond for both of the oxygens, and then you have water. So because this question says use bond enthalpies, we're going to use the formula bonds broken minus bonds formed. So the first thing we need to look at is what are the types of bonds being broken. So if we look at CH4, we have 4 CH bonds. And then we have our oxygen. And so it's an oxygen double bond. Now I need 2 of those though because of our coefficient. So we have 2 double bond O that need to be broken. And that takes care of all the bonds that we have to break. And then we come over here and we look at the bonds that need to be formed. We have CO2, which has 2 C double bond O's. And then we have our water, which has the OH bond, single bond, but we need 2 waters. So we need these 2 plus 2 more to make 2 waters. So we have 4 HO bonds. Then we need to look at our data booklet at section 11, and we need to pull off the types of bonds from here. Well, single bonds are up here in this chart, so we're going to look at carbon and hydrogen is 414. The double bonds or multiple bonds are down here at the bottom, so if we look at our oxygen, that's 498. Then we have carbon and oxygen double bond, which is 804. And we have the hydrogen-oxygen single bond of 463. So we're going to plug those values in, and then we just take our calculator and calculate it, and we get a negative 808 kilojoules per mole. So that negative value tells you that this is an exothermic reaction. We didn't need as much energy to break the bonds than that we got from forming the bonds. So forming gave us more energy than was required to break the bonds. Let's look at another example. This one's a little bit harder because of having to draw the Lewis structures. It tells us that it's a cyclohexane. Cyclo means that these 6 carbon atoms are going to form a ring of sorts, and then we can bond our hydrogen. Remember that carbon has to have 4 bonds. Carbon always has 4 bonds. So when we group them up, we can put 2 hydrogens on each carbon until we get to the last 2. Each one would have a single hydrogen, and we would have that double bonded carbon. Then we have our hydrogen over here for the cyclohexane. We no longer need that double bonded carbon because we can have all of our carbon satisfied with 2 hydrogens. So then we have to look at bonds broken minus bonds formed. So first let's look at our broken bonds. Well, we have 10 hydrogen-carbon bonds. And then if we look, we have 1, 2, 3, 4, 5 carbon-carbon bonds, single bonds. And we have 1 carbon-carbon double bond. Then we have our hydrogen single bond. So we got to break all of that, and then we can put it back together over here. So now we have 6 carbon single bonds, and we have 12 hydrogen carbon bonds. Now you could now look at your reference table, section 11, and you could plug in the numbers. You might also notice that you have some similarities of bonds broken and bonds formed. So we could go ahead and cancel out the redundancies here. So our 10 carbon hydrogens are going to cancel out all but 2 of them on this side. Our 5 single carbon bonds are going to break all but 1, or cancel out all but 1 on this side. So really what's happening is we're breaking this double bond, we're breaking the single bond of hydrogen, we're creating an extra carbon single bond, and we're creating 2 extra carbon hydrogen bonds. So we only really need those 4 values. So then we go look at our data table. Carbon-carbon double bond is 614. Hydrogen to hydrogen is 436. Carbon to carbon is 346. And carbon to hydrogen is 414. So we're going to plug those values in, calculate it, and we get negative 124. So again, this is an exothermic reaction because it gives us that negative value. It's not as exothermic as our first example, but it's still exothermic. Don't forget your unit. Some of you are leaving that off in your classwork. Let's look at one more example. Hydrazine. So we have nitrogen and 2 nitrogens and 4 hydrogens. So our nitrogens are going to be bonded together. Carbon has to have 4 bonds. Nitrogen has to have 3 bonds. So that gives the 1 between the 2 nitrogens, and then each nitrogen is bonded to 2 hydrogens. So that its Lewis structure looks like this. We have our diatomic oxygen, and then on the other side, our diatomic nitrogen is a triple bond, and then we have our water. So then we look and see what are the bonds broken and what are the bonds formed. So first we have a single nitrogen to nitrogen single bond, and then we have 4 nitrogen-hydrogen bonds, and we have 1 oxygen double bond. To form, we need to form a triple nitrogen bond, and we need to form 2 water molecules, each one containing 2 hydrogen-oxygen bonds. So that's a total of 4 hydrogen-oxygen bonds. Then we look at our data table to get our numbers. Nitrogen and nitrogen is 158. Nitrogen and hydrogen is 391. Double bonded oxygen is 498. Triple nitrogen is 945. So see, the triple bond requires more energy to break, 945. Then we have our oxygen and hydrogen of 463. So we plug those values in, we calculate, and we get negative 577 kilojoules per mole. So again, don't confuse this with how you do enthalpies of formation. Enthalpies of formation, bonds are as products minus reactants. Bond enthalpy is bonds broken minus bonds formed. The other thing that goes along with section 5.3 is ozone depletion. Because we're calculating how much energy is needed to break the bonds, we can talk about the ozone, we can talk about how it's formed and how it's depleted and what the balance should be. So oxygen is present in 2 forms. So it has allotropes. You have your normal oxygen, you have your ozone. Both of them are important. Oxygen, O2, is found more commonly than the ozone, O3. Bonds in both can be broken if they absorb UV radiation. So that's how it's actually done in the atmosphere. Is by absorbing that UV radiation from the sun, which is what we want. We want it to absorb that UV so we aren't exposed to as much UV radiation. Since oxygen requires a double bond, it's going to need more energy to break than the 1.5 bonds of ozone. Now, how do we know how much or what the wavelength is for the UV in order to break the bonds? We use Planck's constant. We did these formulas last year. We're not going to do any of this math this year. What's important to know is that the stronger the bond is, the shorter the wavelength is needed, because the shorter the wavelength means the more energy that wave has. So when we say oxygen is a stronger bond, oxygen is going to need a shorter wavelength than ozone needs in order to break the bond itself. All right, so in the stratosphere, that's the part of the atmosphere this is taking place in, you have high energy UV radiation. This, remember, is our symbol for wavelength. So it's a wavelength less than 242 is needed to break the oxygen double bond. And when that oxygen breaks apart, it forms 2 radicals. All that means is it's an oxygen who's looking to form a bond. So it's the oxygen with a lone electron. And radicals are very reactive. Radicals are not something that is stable that we typically find. So the oxygen breaks and forms these 2 radicals. Then the radical reacts with another molecule of oxygen, and that's how we form ozone, O3. Now that is an exothermic step. So here we absorbed energy, now we're releasing that energy. Ozone is weaker, so if we want to break apart ozone, we need a wavelength that's less than 330, so a little bit longer of a wavelength because we need less energy. And we can break that apart into the radical and the oxygen. So oxygen molecules then can react with, or the ozone can react with a radical to form 2 oxygen molecules. So it can do either of these 2 scenarios. It's an exothermic, another exothermic step. It produces heat, and that's what helps maintain the high temperatures of the stratosphere, or that's why the stratosphere has a higher temperature, is because of these bonds breaking and these bonds forming and it being a very exothermic reaction. So the Chapman cycle is what we call that cycle of oxygen forming ozone and then ozone reforming the oxygen. It stays constant if the rate of formation is balanced by the rate of its removal, so it's a steady state. What we find is that we get in trouble when it's no longer the steady state, and that's when we start seeing the issues with the ozone layer and the amount of ozone that we have. So this cycle can show you how dangerous UV light is, or how dangerous UV light is absorbed by our oxygen and our ozone, and how both of those help keep us safe here on the ground level. So that's the end of Unit